Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This video introduces real-time object detection using YOLO11 from Ultralytics on a Raspberry Pi 5 single-board computer. You Only Look Once, YOLO, was introduced by Joseph Redman, Santosh Divala, Rosh Gershik, and Ali Farhadi in 2016 at University of Washington, Seattle, the premier party school where research does indeed have a place to grow. YOLO V8, introduced by Ultralytics in 2023, uses a new training methodology, data augmentation techniques, and model architecture. It achieved state-of-the-art performance across various object detection benchmarks. Ultralytics has now released YOLO11 with vanguard improvements in architecture and training methods. YOLO has consistently pushed the envelope of real-time object detection, making it a popular choice for diverse applications including, but not limited to, autonomous driving, surveillance, robotics, wildlife management, and much more. Its evolution has been marked by significant advancements in accuracy, speed, and efficiency. To help new users ramp up the learning curve, the founders of Ultralytics routinely answer questions on simple and advanced topics at their public forum and technical support websites. The introductory narrative in the first few slides has been culled from the Ultralytics YOLO11 website documentation. The link to the website is posted in the description to this presentation. This presentation examines YOLO11 on a Raspberry Pi 5 computer for basic object detection. A very important disclaimer: it is beyond my limited knowledge to discuss the internals of YOLO architecture. I am still learning step by step on using convolutional neural network, CNN, so I'm a very long way off from digesting YOLO architecture. This timeline illustrates the rapid pace of YOLO releases. YOLO V1 in 2016 introduced the concept of single-stage object detection. It achieved real-time object detection with reasonable accuracy. YOLO V2 in 2017 introduced improvements like anchor boxes, multi-scale training, and higher resolution input images. It significantly improved accuracy and detection speed. YOLO V3 in 2018 utilized feature pyramid networks, FPN, to predict detections at multiple scales. There were further enhanced accuracy and speed. YOLO V4 in 2020 incorporated various techniques like data augmentation, bag of freebies, and bag of specials. It achieved state-of-the-art performance in object detection. YOLO v5 in 2020, developed by Ultralytics, a popular open source implementation that focused on simplicity and efficiency. It achieved competitive performance with less complex architecture. YOLO v6 in 2021 introduced a new backbone network and NEC architecture. It further improved accuracy and speed. YOLO v7 in 2022 enhanced training strategies, model scaling techniques, and training data augmentation. It achieved state-of-the-art performance in terms of speed and accuracy. YOLO v8 in 2023 introduced a new training methodology, data augmentation techniques, and model architecture. It achieved state-of-the-art performance across various object detection benchmarks. YOLO v10 in 2024 represents the state-of-the-art in object detection, achieving lower latency with fewer parameters. It achieves higher performance than previous YOLO models. And now, YOLO11 in August 2024. The YOLO series has consistently pushed boundaries of real-time object detection, making it a popular choice for various applications like autonomous driving, surveillance, and robotics. Its evolution has been marked by significant advancements in accuracy, speed, and efficiency. YOLO11 introduces several significant advancements over its predecessors. Some of the new and improved features include enhanced feature extraction. YOLO11 employs an improved backbone and NEC architecture, enhancing feature extraction capabilities for more precise object detection. Optimized efficiency and speed. Refined architectural designs and optimized training pipelines deliver faster processing speeds while maintaining a balance between accuracy and performance. Greater accuracy with fewer parameters. YOLO11 achieves a higher mean average precision map on the COCO dataset with 20% fewer parameters than YOLO v8, making it computationally efficient without compromising accuracy. MAP is an important benchmark for computer vision tasks in deep learning. Adaptability across environments. YOLO11 can be deployed across various environments, including edge devices, cloud platforms, and systems supporting NVIDIA GPUs. As you can see for yourself, it runs on a Raspberry Pi 5 computer without hiccups, but of course, I cannot compare the performance with a higher-end workstation. Broad range of supported tasks. YOLO11 supports diverse computer vision tasks such as object detection, instance segmentation, image classification, pose estimation, and oriented object detection. In order to provide a quick introduction to YOLO, we will hop around selectively. And as the saying goes, enjoy the low-hanging fruits. In other words, we will use YOLO for basic detection of objects. However, YOLO is a versatile framework for deep learning models. It spans from building models through training and validation to deployment in real-world applications. YOLO uses the term modes to categorize the phases in the life cycle from collecting and labeling data to training and eventually onto deployment. Each phase in the list of modes is a natural progression as shown on the slide. Train fine-tunes your model with custom or preloaded datasets. Val is the important checkpoint to validate the model performance. Predict is what we will focus on in this presentation. Export makes the model ready for deployment in a rich variety of external formats. Track extends the model for real-time tracking applications. Benchmark will help you to understand the speed and accuracy of your model in varied environments of your choosing. YOLO supports basic computer vision tasks to perform detection, image segmentation, classification, pose estimation, and oriented object detection. Detection naturally is the most fundamental task in computer vision processing. Boxes are drawn around the detected objects, and the objects are classified into categories. YOLO can detect multiple objects from a rich set of diverse sources. YOLO segments an image into different regions upon detection. This task has many contemporary applications in medical imaging, autonomous driving, robotics, urban planning, and much more. Classifying images based on content is useful, for example, in diverse applications such as security, inventory management, and agriculture. The classic benefits of pose estimation are commonly found in athletic games, crowd management, and healthcare monitoring. Sometimes images are not presented for processing in a preferred orientation. Oriented object detection introduces an extra dimension to detect rotated objects. To stay within self-imposed time constraints for a single presentation, we will confine our demonstration of modes to predict only. For the predict mode, we will demonstrate all the tasks listed on the slide. The primary goal of these exercises is to demonstrate that the Raspberry Pi 5 computer, notwithstanding its limited computing resources, is fully capable of supporting some of the basic YOLO operations. YOLO models are versatile and support a wide range of computer vision tasks, including but not limited to object detection, instance segmentation, image classification, pose estimation, and oriented object detection. With this slide, we are going to rush through some simple examples of the basic tasks. Let us not focus on the code as much as on the basic operations of the tasks. A few slides later, we will step through the basic construction of a script for a task in its simplest structure. You can then revisit the scripts for a better understanding of the code. We will illustrate object detection first, since identifying and locating objects within an image is at the very heart of YOLO. Before we begin the first demonstration, let us review the development environment briefly. We will be using PyCharm from JetBrains. You can use any other integrated development environment, IDE, that you are most comfortable for your work. Let us search for the JetBrains Toolbox app with our browser. Having navigated to the site, select the download option, keeping in mind your development platform, Windows, Mac, Linux, or even Linux ARM64. Once you have installed that, you will see a toolbar button. For this demonstration, we have installed the JetBrains Toolbox app previously. It can reside as a toolbar button if you wish. Select PyCharm from the toolbox, and if you have not installed it, it will start installing immediately. If you have already installed it, it will launch the corresponding PyCharm IDE. Please pay attention to the version of PyCharm that you choose to install. There is the educational license that is free to registered students and educators. And then there are variations of the professional license where you have to fork over money. I use the free open source software FOSS version, also known as Community Edition. The reason I'm spending a few minutes on the toolbox is because updates to PyCharm through the toolbox are painless. The best way to update or upgrade your PyCharm installation, irrespective of the license you have chosen. So here I go ahead and launch PyCharm Community from the toolbox. So here's my PyCharm screen, and I'm going to go ahead and clone a repository. So click on the clone repository and plug in the URL for the repository. I do have a YOLO11 repository already created. It's basically a skeleton repository with nothing much in there, and we're going to start go ahead and build all our Python scripts in there. So click on clone, and as you can see, it'll take a few seconds to go ahead and build. Now, one of the things that you may notice that it's gone ahead and configured a Python interpreter. If it does not, then you will have to go in manually and configure it, and also specify whether you need a virtual environment or not. Now, in my case, I have already done that previously as for packages, so I'm pretty much safe in assuming that my interpreter is correct and that I have some of the basic packages. Now, obviously, I don't have YOLO Ultralytics package installed, and that's what I'm going to show in the next few steps. Now that we have cloned the repository locally here, let's go ahead and set up the Python interpreter. So under File, we click on Settings, and lo and behold, we see that we have some invalid configuration. So all we want to do is click on Add Interpreter, and we will add a local interpreter that is specific for this purpose in here. And we want to create a new virtual environment for this repository. And we're going to use the base interpreter 3.12. So we go ahead and click OK, and it should go ahead and start installing the interpreter. Now that we've configured our Python interpreter and the virtual environment, you can see there's an entry for venv. Let's go into this folder called predict and take a look at this file called hello YOLO py. And it's a very simplistic example just to get started in the style of hello world. So I import the Ultralytics package and specifically the YOLO module. I define a pre-trained model from Ultralytics, and then I use an Ultralytics image file for the detection. So as you can see, there are some squiggles, which means there are some unresolved extensions, and we'll go ahead and fix those in a minute. So we notice right away that the Ultralytics package has not been installed, and that's why it's flagging it. So we go to the context menu and select Install Package Ultralytics. It's going to ask us for confirmation, and we go ahead and say yes. And at the bottom in the status bar, you can see that it's taking the steps to install it. It's going to take a while, so I'll stop the video and resume once it's installed. So you can now see the confirmation message that the package has been installed successfully and the squiggies have gone away. There's one thing that I'd like to mention right away is that I've made a remark in here about the models that will be downloaded when you're running this. These are .pt files, and similarly you will have some test image files. You don't want these to go back to the GitHub repository. So make sure that you update your gitignore. And right at the bottom of gitignore, I've got some classic files in here. I don't want to upload the video and the image files, and I don't want to upload the commit rather and push the .pt, these files. So I put them in gitignore, and you will see likewise when they're downloaded from the Ultralytics site, they don't get uploaded to the repository. So now we're ready to run this. So it's very straightforward. We just click on run and let it zip through very quickly. So initially it's going to go ahead and download both the model as well as the image, and now you can see that as soon as it's done that, it's giving us confirmation that it found 4 persons and 1 bus, and this is using the nano model, the 11N. We'll dive into some of the other models, and you'll see some differences in detection, and we'll discuss all that. All I wanted to show you here was that now we have YOLO11 running with a hello world exercise, and we'll now take it to the next step. Let us use a simple Python script to demonstrate basic object detection. So I will launch PyCharm IDE on my Raspberry Pi 5 and wait for it to load up before we proceed to the script. In the main window, I do have the script, and I'd like to highlight the 4 key essential statements that one would need to perform basic object detection. First of all, we need to employ the Ultralytics package. Secondly, we need to define the model that we want to use. And on the line above in the comments, I've listed the suffix letters for tidiness: N for nano, S for small, M for medium, L for large, and X for experimental, with the prefixes YOLO11. So YOLO11N.pt is the Ultralytics model name and file for the nano model of the pre-trained COCO dataset which we're going to use. We define the source and we pass the source to the instantiated model object, and that's all we need. And now if we run this, we will get the image displayed on the screen. So I'll go ahead and click for the nano model. And at this stage, what I'd like to point out is let's not pay attention to the confidence values. Just look at the results in general as a qualitative thing. And as you can see here, it ran the result. It found a few boards and some people. But notice that there are a couple of things missing that we would have normally expected. And that is obviously the case for a nano model. So let's go ahead and change the suffix letter to S so that we can now use the small model for object detection. And again, we'll run this and it'll take a few seconds because it's the Raspberry Pi 5. Maybe later on we'll summarize the results. But now you can see more boats were detected and a potted plant was detected too. So let's move on to the medium model and see if we get some more objects detected. And all we have to do in this script is just change the name of the model because the source file remains the same. And it'll run again and wait. Took a little longer, but now you can see more boats have been detected and a person has been detected on the right side of the bank. So we'll now apply the large model and run it. And hopefully, we'll be able to see some differences between the medium model and the large model. Of course, the large model takes a little more computing resources. And what I'd like to point out here is that a handbag was detected, which was not detected in the previous models. And not just one person, but more persons. So definitely the large model has something going for it. Now let's move on to a little more larger model. And instead of calling it extra large, they call it experimental. And the letter for that is X. And it takes more computing resources, but let's go ahead and run it. Later on, when we continue with the presentation, we will have a summary slide comparing the models in a quantitative manner. For now, I just want to give you a feel of the 4 basic steps to do object detection and then the differences between the models in a qualitative nature. You can see that in the experimental model, the handbag has disappeared. Most of the other things have remained. So please try to understand that modeling and object detection require a bit of babysitting. Instance segmentation is a computer vision task that involves both object detection and semantic segmentation. It aims to identify and segment each individual object in an image. Object detection identifies and localizes objects within an image by drawing bounding boxes around them. Instance segmentation not only identifies the bounding boxes, but also delineates the exact shape of each object. YOLO instance segmentation models provide masks or contours that outline each detected object. This is particularly useful for tasks where knowing the precise shape of objects is important, such as in autonomous driving, warehouse operations, robotics, and remote sensing. Instance segmentation is for the detection of objects and delineating their boundaries. Instance segmentation extends object detection by identifying individual objects in an image and segmenting them from the rest of the image. The output of an instance segmentation model is a set of masks or contours that outline each object in the image, along with class labels and confidence scores for each object. Instance segmentation is useful to establish the objects are in an image and their exact shape. Let's take a look at a simple example of segmentation as applied in a search and rescue operation. So we have an image here of people on the beach, and we're really trying to locate a missing dog. And so there are people walking down a trail and trying to locate the dog. That's the image that we're going to apply as source for the search and rescue. As before, we will import the Ultralytics package, and now notice that there is a slightly different model naming convention from Ultralytics. So the COCO dataset was YOLO11N. In the case of a pre-trained segmentation model, Ultralytics is providing a suffix dash SEG for segmentation as the model name. So the model name is YOLO11N-SEG, YOLO11S seg. We're going to stick to just the nano model in the interest of time and just run this. So we instantiate the model object, we give the reference object that I just showed you just now, the source file, and then we pass it on to the model. So let's run it and see what we get. So the model file, if it is not present, will be downloaded. And in this case, obviously, it's already present, so it's been downloaded. And it's gone ahead, and you will notice that in here, if you run this example, it didn't consider that object to be a dog, but a sheep. So in reference, an animal, a four-legged animal. But you can see we're not trying to find out anything more than looking at the shapes of the objects that we have detected. And this can be very useful when applied in a broader context if somebody is trying to build an autonomous vehicle to see if pedestrians are crossing or there are objects, and based on the segmentation, take corresponding action. Let us take a closer look at instance segmentation. Let us choose just 3 of the many disciplines where this technique may be useful. Autonomous vehicles, robotics, remote sensing are some of the many disciplines where image segmentation can be very helpful in supporting decisions. For autonomous vehicles, instance segmentation helps self-driving vehicles accurately detect and track individual objects like cars, pedestrians, and cyclists. By understanding the precise boundaries of objects, self-driving vehicles can make better decisions about navigation and collision avoidance. When instance segmentation is applied in robotics, robots can grasp and manipulate objects more effectively by understanding the precise shape and location. Instance segmentation enables robots to perceive and interact with complex environments. Instance segmentation, as applied to remote sensing, can help classify different land use types, such as urban areas, agricultural land, and forests. Identifying and counting specific objects like vehicles or buildings in satellite or aerial imagery. Image classification categorizes images into predefined classes. Image classification is the simplest of the three tasks and involves classifying an entire image into one of a set of predefined classes. The output of an image classifier is a single class label with a confidence score. It is efficient when the location of the objects and their corresponding shapes are superfluous for the task at hand. Let us look at the code snippet for classification. So again, we will have to import the YOLO package, and then we define a model name. And the model name, in keeping with the Ultralytics convention, they use -CLS as the suffix when applying it to classification models. So YOLO11-CLS, YOLO11S-CLS, and so on and so forth. So we define the name. As I've said before, we'll stick to the nano model, and then we give it an input source, in this case an image of birds, and then pass it on to the model instantiated for the results. So let's run this, and in a few minutes we'll get the output displayed on the screen, and then I'll present it in a slightly different way for you to understand. So it's run the model, it's displayed it, and now you can see that instead of drawing boxes around the detected objects, it immediately classified it correctly with 100% accuracy, a macaw. So the two birds are macaws. It's not really wasting its time on any of the others. Flamingo, the 0%, lorikeet, cock, and toucan are 0%. So this is very useful when you want to know with some confidence what are these objects. And so for classification purposes, you will use a pre-trained or train it yourself, leveraging YOLO's pre-trained model for classification. Pose estimation is applied to detect and track key points on human bodies. Pose estimation identifies the location of specific points in an image that are called key points. These key points represent parts of the object that are distinctive features. The locations of the key points are represented as a set of 2D, X and Y, or 3D, X, Y, and visibility status coordinates. Pose estimation is a very helpful feature to identify specific parts of an object in an image and their location in relation to each other. Let us take a quick look at pose detection using a pre-trained Ultralytics model. So again, the code snippet is exactly the same. We import the Ultralytics package, and then we select a particular pre-trained Ultralytics model for pose detection. Ultralytics uses the convention -POSE for pose as a suffix to their pre-trained models. So YOLO11N-pose.pt is the pre-trained nano version of the pose model. And then we have the source image that I just want to quickly show you so that you can see what's going on in here. And the image is the courtesy of essentialsports.com from the Tokyo Olympics. Then we feed that information using the model entity and collect the results. So let's go ahead and run the code snippet, and we'll say run post predict. And if the model has already been downloaded, it shouldn't take too long, and here we are. So a couple of things to note. Obviously, the other subjects are also detected as persons, and their eyes and shapes and so on, limbs are drawn. But the principal focus is on the two wrestlers. And you can see only one wrestler was detected, and the other one, because it's at a different angle, it didn't get detected. So it's a shortcoming of this model, and maybe we can explore other models, and a little later we will do oriented object bounding, where the problem may resolve itself. Oriented object detection, OBB, permits the detection of objects with rotation for higher precision. Ultralytics does provide a broad range of pre-trained general-purpose models, as well as some special models for specific solutions. Naturally, there is ample guidance at the Ultralytics website on training one's own models too. Let's take a look at the code snippet for oriented object detection. It's going to follow the same principles for 4 statements, which is to import here the YOLO. And then the model is now -OBB. And we're going to use the large model specifically because it may be a little tougher to use the nano model for the image that I have. And then, of course, the source image. And let me just show you the source image. It's for a tank farm from an aerial view. And the key things here to notice that there are a lot of objects here at oblique angles that hopefully should show up as being detected. And then we feed that to the instantiated model object in here. And so let's run this. And if we run this, if the model is downloaded, it shouldn't take too long, even though it's a large model. And hopefully it'll give us some meaningful information. So what I'd like to do is interpret the results a little bit for you to show you the difference in oriented objects. So normally what we get, the rectangular boxes that you've seen, are in portrait or landscape mode. They're rectangular basically. But here they're slanted. You can see the ship is slanted. The ship here is slanted, the pier, which is represented as harbor, and then there's a bridge. They're all slanted at different angles. And obviously, you can use the key points to find out the orientation angle, which is another important property that you can use for your own use. And this is an example of oriented object that we can look at when we're detecting models, using preferably the larger models because they have more refined data. Having taken a quick look at some basic YOLO demonstrations in the previous slide, let us now drill down into predict mode using the smallest pre-trained model available in YOLO11. Ultralytics prepared a family of models using the Common Object in Context (COCO) dataset. These models range from nano to small to medium to large and even experimental. We will confine our demonstrations to using the nano model. The nomenclature by Ultralytics for these models is YOLO11 followed by a letter. For the nano model, the name is YOLO11n.pt with the file type extension .pt referring to its pre-trained designation. It is best to sustain the enthusiasm for YOLO11 by illustrating the ease of use of the solution with familiar objects. In a later tutorial, we will cover how to train a model, either from scratch or leveraging a pre-trained model with one's own objects and then applying the model for the key tasks in YOLO. What does YOLO11 offer for model prediction? Ultralytics uses the term predict mode for this feature. It is designed to be used without prior knowledge of any deep learning techniques. Just provide the input data, select the processing options, and then use the results in a variety of formats for instant display or further processing in an arrangement that is commonly referred to as pipeline. There is an important app called RoboFlow that dovetails with YOLO11 very nicely. Again, we will cover that app in a future tutorial. What are the benefits of YOLO11 Predict Mode? It is versatile. It is capable of making inferences on images, videos, and even live streams. It performs rather well. It is engineered for real-time, high-speed processing without sacrificing accuracy. It is easy to use. There are intuitive Python and command line interfaces for rapid deployment and testing. It can be customized. There are numerous settings and parameters to tune the model's inference behavior according to your specific requirements. In order to hit the ground running, let us perform a classic Hello World exercise with Predict Mode. The first choice that needs to be made is naturally the source of the input data for use during Predict Mode inference. The extensive list of choices have 4 different groups: individual images, collection of images, recorded video files, and live video streams. The second choice is particularly important for video input sources. To stream or not to stream is the question. By setting stream equal to true, we let YOLO11 generate a memory-efficient results object for downstream use, especially when faster processing is desirable. The list of inference sources is listed at the YOLO11 website and partially reproduced at the repository of test cases for this presentation. The third choice is whether streaming will be used or not. If stream is equal to true, then a memory-efficient representation of the results object is prepared. This setting is desirable for video streams. Of course, it is important to establish a good understanding of the advantages and limitations of the pre-trained models in YOLO11. In addition to the classic versions of the COCO dataset in the models by Ultralytics called nano, small, medium, large, and experimental variations, Ultralytics provides other specialty models for ease of use by beginners. We used some of these models in the previous demonstrations without discussing the models themselves in any detail. Again, there is provision for training one's own model, to which we will examine in a later presentation. For the limited purposes of this presentation, we will iterate through each of the basic pre-trained models: nano, small, medium, large, and experimental. There are other several runtime parameter selections. We will explore only the ones that we will use in our tests. Finally, the results object can provide very rich information that we will explore incrementally as we drill down predict mode with our test images and videos. Let us use the simplest example to hit the ground running. Let us perform a classic Hello World exercise with predict mode. We will limit ourselves to basic object detection only. There are 3 fundamental steps with a 4th step to drill down with the results object. The first step is to import the Ultralytics package. We will view the Python script shortly. At that time, we will examine some basic recommendations regarding the use of Python packages in an environment where diverse work is performed. The next step is to select a model for the object inference. In this example, we will use the nano model that has been pre-trained by Ultralytics. Again, we will discuss the choice of models a little later in this presentation. The penultimate step in this example is to invoke the inference with a source input. For this test, we will use an image that has not been used in training or validating the chosen pre-trained model. As you progress along the learning curve, you will understand the importance of the last statement, especially when you are engaged in training your own models. You should never test the model using input data that was used in training and validating the model. Finally, after the inference is complete, the results object is available for inspection. In this test, we will simply satisfy ourselves by viewing the output image. As you will realize after completing this test that you are looking at an iceberg floating above the water. The work performed by YOLO11 is beneath the surface. Time permitting, I would like to provide the proverbial 100,000 feet overview in a later slide or two. There are 4 fundamental steps with a 5th step to drill down with the results object that is omitted from the slide. We will explore the drill down options later. The first step is to import the Ultralytics package. We will view the script in an integrated development environment, IDE, shortly. At that time, we will examine some basic recommendations regarding the use of Python packages in an environment where diverse work is performed. The next step is to select a model for the inference. In this example, we will use the nano model that has been pre-trained by Ultralytics. Again, we will discuss the choice of models a little later. If the script does not find the pre-trained model in the current folder of the run, it will download it from the Ultralytics site. The penultimate step is to identify the input data for the object inference in the predict mode task that is implied in the absence of other parameters. A wide variety of images and videos are permitted in this mode. We will use the standard bus.jpg image file. We will reference the image using an URL to the Ultralytics site since this image may not be present in the current folder for the first run. The inference is performed in the final step. The results object may be inspected further after the inference is complete. In this test, we will simply satisfy ourselves by viewing the output image. As you will realize after completing this test, you are looking at an iceberg floating above the water. All the processing performed by YOLO11 is beneath the surface. Time permitting, I would like to provide the proverbial 100,000 feet overview in a later slide or two. Of course, there are other analogies too, like a swan floating gracefully on a river while its feet are paddling furiously beneath the surface of the water. This analogy was very popular during the early days of client-server database techniques. Now that we have run YOLO11 using a Python script in the spirit of a Hello World exercise, let us quickly take a look at the equivalent operation from the command line in a console terminal window. The Ultralytics command line interface, CLI, enables simple single-line commands to be run without the need for a Python environment. CLI requires no customization or Python code. You can simply run all tasks from the terminal with the YOLO command. Check out the CLI guide to learn more about using YOLO from the command line. The basic syntax for the command is shown on the slide. It is YOLO followed by a task and a mode and then the optional arguments. The command is YOLO. The task parameter can be any one from the list. Similarly, the mode parameter can be any one from the list, subject to its availability for the chosen task. There are too many options in the args parameter to discuss on a single slide here. Please consult the Ultralytics documentation for the details. In the example listed on the last line of the slide, there are two examples of the args parameter. The model is specified in the keyword equal to value pair syntax. Similarly, the input data source is specified as a keyword value pair too. Let us run an example using YOLO CLI. The structure of the command is YOLO, task, mode, and then arguments. Task for our Hello World exercise is detect. Mode for our Hello World exercise is predict. The first parameter, model equal to YOLO11n.pt, selects the nano model. The second parameter specifies the source for the predict mode operation. Let us use bus.jpg from the Ultralytics website as the source image. The second parameter can be represented as source equal to bus.jpg with the full URL enclosed in quotation marks, of course. The actual command that we used to type at the terminal window prompt is YOLO predict mode model equal to YOLO11n.pt and then source equal to open quotes https://ultralytics.com images.bus.jpg close quote. It doesn't take YOLO too long to return the expected output, one bus and 4 persons, as we saw in the Python script. Ultralytics solutions provide vanguard applications of YOLO models, offering real-world solutions like object counting, blurring, and security systems. These solutions enhance efficiency and accuracy in diverse industries. Discover the power of YOLO11 for practical, impactful implementations by visiting the link on the slide for more insightful information. What are you waiting for? The results from the predict mode exercise using a Python script will return a result of results objects. There are 2 considerations for the results object: attributes and methods. It is important to understand that attributes have objects, which in turn may have attributes and methods. The Ultralytics documentation does an excellent job in enumerating these properties. As a side note, the advantages of using Doxygen for documenting source code is self-evident when you browse the Ultralytics website. The results from the predict mode exercise using a Python script will return a list of results objects. There are 2 key considerations for the results objects: attributes and methods. Let us drill down the results object for a few key attributes. Some of the objects in the results object will contain values only if corresponding models are used. Please consult the Ultralytics website for the range and scope of the pre-trained models. Of course, you can always train your own models, as we will discuss in a future tutorial. A key object in the results object is boxes, which can be used to index, manipulate, and convert the bounding boxes to different formats. We have demonstrated the use of conf and CLS in our Python script to return the confidence values and the name of the detected objects. You may want to save the coordinate points in one of the available formats for further processing in your own scripts. The masks object can be used to index, manipulate, and convert masks to segments. The class methods and properties are useful to transfer the inference results for downstream processing in a workflow. The key points object can be used to index, manipulate, and normalize coordinates. The probs object, when available, can be used to index, get top 1, top 5 indices, and scores of classification. The oriented bounding box, or OBB object, can be used to index, manipulate, and convert oriented bounding boxes to different formats. It is important to understand that not all models will be able to provide values for some of the child objects of the results object. For example, if we are using YOLO11N nano model, then there will be no values in the object results probs. In Python, the value is none. This model, YOLO11N, is purely for object detection. To obtain probabilities, it will be necessary to use a classification model. The equivalent Ultralytics model for this purpose is YOLO11N-CLS. If the original model is replaced with this latter model, then results.probs will have probability values in a curated set for the topmost, for the 5, and the top 10 also if available. Ultralytics has published the full range of pre-trained models at their website. The results object has a plot method to customize the output. This is not just eye candy, but also helps with consistency in presentations to a diverse audience. Let's take a quick look at how we can optimize the plot information that YOLO11 displays. So I have a simple sketch developed here, and I have two images that I'm going to use for prediction, and then allow the plot feature to go ahead and display the information to the user. So it's pretty straightforward. Just identify the images, run predict, and then let it run. So once it runs, it'll create successive pages of images that you can see. It's using a slightly different representation for the display. And in each of these cases, you can go ahead and optimize your settings. To ensure that YOLO models running in parallel do not interfere with one another, YOLO supports thread-safe inference. This mode guarantees that each thread's predictions are isolated and do not interfere with each other. This guarantee avoids race conditions and ensures consistent and reliable outputs. Here is a summary of the guidance. Run each thread with its own YOLO model instance. Use Python multiprocessing module to avoid unintended locks and risks. Rely on YOLO for concurrency. Let's do a simple demonstration of multi-threading. I have a simple sketch here, and basically we're still using the nano model. And as in the previous demonstration, we'll stick to the same two image files so that you get a feel for the response time and the throughput. So it's these two files, and we are launching them in separate threads as shown here. So let's go ahead and run this. And when we run it, you can immediately realize that the speed at which it does the processing is much faster than the example that we just saw a little while ago with plot predict. And of course, because of the sizes of the images, the processing order is slightly different. You can see that it did the 15 megabyte file first, and then it did the 19 megabyte file. So again, very, very quick introduction, and I hope you get a chance to experiment with threading, because that'll make life much faster for you on the Raspberry Pi 5. Now that we have some understanding of how to use the results from YOLO, let us quickly run some additional tests to illustrate just a few ways to get started quickly with only YOLO. We will construct simple examples to illustrate these results. First, let us look at multiple input files, and instead of sequencing these, run them together. Let's demonstrate how we can specify multiple files for the inference. So here in this example, we have just one file, and what I'd like to do is replace this with multiple files. So it's basically just an array, and I've got two other files added in here. That's all it takes, and nothing else in the code would change. YOLO will recognize that this is now a list of files and go ahead and process all of them. Similarly, we can change the reference from the image to a video. And we can pass this without any other modifications to the code. YOLO will recognize this is a video file and process it accordingly. For counting, we define a rectangular or a line through which the objects will pass, and we report on the classification of the objects and how many came in and how many left. As you can see, we had 3 suitcases leave the rectangle, and so the count here is a 3. Sometimes it'll not recognize the image properly and classify it incorrectly. But so far, it's been all suitcases coming in and leaving, and we've already had 6 suitcases leave that rectangular area. Notice there are people being recognized and classified, but they're not being counted. Only objects within the rectangle are being counted. Objects outside the rectangle are not counted. In this segment, we're looking at a short introduction to analytics tracking using YOLO. So the wildlife management is training elephants to avoid collision with trains. So as soon as the train approaches the elephant is being steered away, and this is of course being under training, but generally the elephants will not be mounted by a mahout to move them away from the tracks. They have to recognize how to move away, and what YOLO is doing here is plotting the tracks the elephant takes under guidance and then trying to use that as a way to train other elephants. This demonstration was left open-ended to illustrate that persons were not being counted in the video stream. In other words, we can expressly specify the classes to be counted as a list. Counting is an important decision support solution for many applications like inventory management, traffic analysis, and consumer environments for shopping and security. The idea in this presentation is not to saturate you with examples, but to help you understand that you can use YOLO11 comfortably for detection and inference. One final but very important observation on the actual results. YOLO11 has several pre-trained models starting from nano to small to medium to large to experimental. The resource demands from nano to experimental models increase, and conversely, we have relied exclusively on the nano model because it is a good fit for the Raspberry Pi 5 computer. Please do not form any opinion on the accuracy of the model for your specific needs, except to understand the general trend from nano to experimental with other models in between. The classification labels improve in accuracy with the larger models. It is simply a case of changing the model name string value in the code to change to another YOLO11 pre-trained model. I sincerely hope that you will use the other models too and evaluate them. It is relatively easy to start your learning journey with YOLO11 on a Raspberry Pi 5 computer. You can progress to faster and more abundant resources as you climb the learning curve. Your Python scripts will still be portable. The support from Ultralytics by way of documentation, tutorials, and technical support is way above excellence. Owing to the vast potential and range of topics that can be covered even in an introductory presentation on YOLO11, it was necessary to confine our review to the predict mode in YOLO11. I hope that this presentation will help you to kick the tires just a little bit more so that you can see for yourself that you only look once. Don't stay on the sidelines. Jump onto the YOLO bandwagon. We will definitely pursue other YOLO topics in the near future. Keep pushing the envelope. You may indeed work in assisting with the future release of You Only Look Once. Go ahead and try YOLO11 yourself without writing a single line of code. The URL is at the bottom of the page, and all you have to do is upload your images or videos to see the results without a single line of code. That's all, folks. Thanks for taking the time to view this presentation. Would love to hear from you with your feedback. You're always welcome to be critical in any which way you can. Until next time, bye for now. This presentation was prepared with assistance from free open source software for the backbone of this video presentation. The key products are Ultralytics YOLO11, OBS Studio, Kdenlive, LibreOffice, and of course Ubuntu. Teachers, viewers, and peers provided valuable feedback. I would also like to make a special mention of the fact that the Ultralytics documentation for YOLO V8 and YOLO11 are exemplary. Everything works as documented. The best part is the founders of Ultralytics answer questions posted by beginners at the forum. This is indeed incredible and perhaps a testament to why we are all excited by the possibilities of the work being performed by Ultralytics. My apologies if I have inadvertently omitted anyone from this acknowledgement. A very big thank you to y'all for the assistance.